Vodka. With this presentation, I would like to give you some insights into my research work of the last 6 years. It is a story about the efforts we have made to introduce wood into a completely new field of application. But to explain the background, let's go back to earlier times when most of the things we used were made of wood. Wooden bows and arrows are highly dynamically loaded, as well as the Romania catapulta shown here. Different types of wood were also used for different working and weapon equipment in the early and late Middle Ages. And even in the Second World War, wood played a central role. Due to the lack of material, wood was used in the production of fighter planes. One of the most successful aeroplanes, the English Mosquito, was built almost entirely of wood. Wood is also essential for musical instrument. The entire historical equipment and complex machines and constructions were produced out of wood until the 19th century. Recent studies show that craftsmen had a high level of empirical knowledge in order to use different wood species optimally for different applications. Within the scope of a dissertation, we are currently investigating the resistance of wood to salt water, and despite thousands of years of experience in sailing across oceans, we have to notice that we have a lot of empirical experience but little scientific knowledge. Tennis has been played for almost 800 years. Since only 40 years, we use other high-stressable materials than wood for producing rackets. In cricket and baseball, the ball hits the racket head at the speed of 160 km per hour. The racket head moves in the opposite direction at more than 180 km per hour. Today we are able to simulate the enormous loads that occur in rackets. Another sport in which the material wood has not yet completely disappeared is golf. Clubs are partly still made of wood today. Inlays of the club head are made out of metal and are glued to the club head just like the shaft. The wood surface is made durable, weatherproof and mechanically resistant by different layers of coatings. The ball is speeded up to 240 km per hour on the tee. In a pilot project, we built different components of the concept car Colt, including the vehicle underbody, which was constructed corresponding a skateboard. Master theses on wooden bicycles were carried out at several European universities, including BOKU. One of the master students made a business out of it and now makes wooden rims. What we should keep in mind when we are looking at the achievement of sport legends and pioneers like Scott and Amundsen is the equipment they used. Wooden skis and sledges were used when they discovered the South Pole. But not only historical sport equipment is made of wood, every modern ski takes advantage of this material. Specially composed wooden cores give the ski strength and stiffness at low mass. The history of aviation is closely connected with the material wood. Even propellers are still made of wood today. The material withstands both environmental impacts and the enormous mechanical and dynamic loads. The first supersonic jet, the Comet, was also a wooden construction. In 1942, Howard Hughes got the order to develop a cargo transporter for the US troops. The famous Spruce Goose has a wingspan of 96 meters and was made of phenolic resin impregnated plywood. There is no doubt that wood is the basis of historic aviation, but is the material also suitable for road vehicles? In older vehicles such as Ford or Chevrolet, several components were built from wood. The crash behavior of these cars does not meet the requirements and safety standards. But were these old cars really crash optimized? Even for the occupants of the famous Beetle made of steel, the chances of survival in a frontal collision were significantly lower than in a modern car. The Volvo XC60 is one of the safest cars. Cruising with an old Chevy is probably much more fun, but in the case of an accident, the chances of survival in a modern SUV are much higher. But does this mean that wood cannot be used in vehicle constructions? With modern active safety, meaning safety systems that prevent accidents, vehicle constructions and safety concept must be reassessed. From this perspective, the use of wood must be reconsidered. In addition to self-driving cars and buses, the urban mobility of the future will also include so-called people movers. What we will find in these moving boxes? Wood. Why? From the moment cars will not longer driven by people, they will start to see the passenger compartment as a moving living room. And living is closely linked to the material wood. Our industrial designers from FH Joanneum were responsible for the participation of Volkswagen R&D department in the wood car project. 2 design studies were carried out by the cooperation with MAN and Volkswagen. 2 concepts for self-driving buses with new wood design aspects were developed for MAN. A part of a passenger compartment of one concept was produced as a mock-up. But isn't level 5 old stuff? At the moment, several companies, also in Austria, are dealing with drones. Transport of parcel with drones is close to the market launch. New projects deal with drones for passenger transport. In this application, autonomous driving meets modern aviation technology. The high performance and lightweight material wood can probably play a central role in this field. In 100 years of aviation history, it has been proven that wood can give a valuable contribution to this sector. Let's take off with suitable ideas towards the mobility of the future. At an intermediate state of development, you may find new vehicle concepts that we have not yet considered, flying cars or other hybrid vehicles. On the internet you will find some amazing objects. I'm convinced that most of these concepts will not be part of the future mobility. Nevertheless, these concepts can possibly contribute to radical innovation in this section. And perhaps these vehicles will include wood as a high performance and lightweight material. But why is lightweight construction an important issue? Because about 25% of the energy required to move a vehicle is related to its dead weight, regardless of whether you use an electric drive or a conventional combustion engine. The range of a car is largely determined by its own weight. With combustion engines, only small improvements in efficiency are possible, but lightweight construction has a much greater influence on energy consumption. However, not only established lightweight construction materials such as aluminum, carbon and glass fiber composites should be considered. Intelligent engineering opens up the possibility to achieve maximum performance at minimum weight. In this sense, wood can make a valuable contribution to future multi-material constructions. Now we have reached the core topic of this presentation. Wood in vehicle constructions. Wood car. This does not mean wooden cars. CAR stands for Computer-Aided Research. We consider hardwood to be most suitable material for such constructions. In recent years we have mainly worked with beech, birch and poplar. It is not our aim to use solid wood elements, such as boards, in a vehicle construction. We rather think in terms of wood hybrid constructions, which consists of layered veneer composites. This is also in line with the solution of other research groups in Germany. But can wood really meet the requirements? There are not only mechanical and crash requirements that have to be met. Cars drive in deserts and are exposed to extreme heat. All functions of a car have to be fulfilled even under extreme conditions and road surfaces. Snow, ice, rainfall, temperature ranging from -40 up to 80 degrees. And it is possible to simulate wood by means of finite element modeling. This question was the first big task we were confronted with. There is no material that finds its way into the car world that cannot be calculated on computer with modern software packages. Modeling and digitalization of wood was heavily discussed 5 years ago at the Styrian Future Day. At this time, the majority agreed that this would not be possible. This opinion was not accepted. A prominent supporter from then until now was Charles Morgan. Morgan Motors can look back on over 100 years of automotive history with wood. These cars consist of an ash wood chassis covered with a thin aluminum sheet skin. In our discussions, Charles has repeatedly claimed that their constructions would even have an advantage over conventional vehicle constructions in the event of a crash. Unfortunately, in this case of a Morgan three-wheeler, there is little to see. For the high impact speed, the Morgan 4 Plus still looks quite good. And at this impact, the Morgan apparently continues to drive undamaged, and the conventional car has to stop because of a severe damage. Other research groups have been working on wooden concept cars before us. However, these research groups have not carried out any calculation and simulation on wooden elements. Our goal was to prove, in cooperation with the University of Technology in Graz and the Virtual Vehicle Competence Center, that it is possible to calculate the mechanical properties of wood. Since the beginning of these research activities, we have been working together with the Weitz Energy and Innovation Center on the processability of wood hybrid components. In the course of the feasibility study performed in 2016, 3 parts of the concept car Kult from Magna Steyr were produced. Instrument carrier, rear panel and the underbody were designed, manufactured, simulated and tested. The aim of the test was not to show that wood is better than other materials in terms of its properties, but that it can be designed and calculated for crash simulations. The comparison between the images taken by the high-speed cameras and the simulation results showed good agreement. With the FE modeling, not only the time of material failure could be predicted, but also the failure behavior and the energy absorption. The simulation is based on material tests to determine the material behavior as well as the material characteristics in plastic deformation and failure. These parameters are determined by means of standard tests, and the simulation is subsequently validated by component simulations. In order to find further partners beside the core partners IB Steiner, Lean and Weitzer Paquet, we contacted the company Matro in snowy Tyrol. The manufacturers of electric Caterpillar vehicles had a clear vision right from the start of the cooperation to develop a new concept of the snowmobile Ardenna. The first version of the vehicle was made of steel and was too heavy. A wooden chassis had to be developed to reduce their weight by more than 100 kilograms without losing performance. For this purpose, as many parts of the vehicle as possible were built from wood. The starting point of the design process was a so-called topology analysis, which was used to find an optimal lightweight structure. The technical design and construction of all components was then already carried out on the computer. Every screw, every connection, every element was subjected to the required loads of the entire vehicle on the computer before a demonstrator was produced. This meant that the development time of the Ardenna, including production, was completed in just 1 year. This would never have been possible with conventional methods. The production was then carried out at BOKU and in Weitz. The individual work steps were precisely documented by the company Lean in order to have calculations available for virtual production layout. In addition to the process engineering knowledge, this creates the basis for a production concept. Colano and EJ provided the adhesives and fasteners, and Weizsäcker-Packett's production staff and almost the entire innovation department were involved in the organization of the production. The assembly of the vehicle was then carried out under the supervision of Matro in Weiz. The elements were coated and glued and screwed together with metal and plastic parts. In some cases, some adjustments were necessary, but basically all elements fit together perfectly for the 3 prototypes. One of the prototypes was then electrified by Matro in the following month and equipped with all other attachments such as seat, handlebars, etc. The first test runs took place directly behind the factory building of Matro, and last winter the first test run were carried out on the ski slope. The calculation from the life cycle assessment showed significant advantages for the use of wood. Only 5% material substitution in the European car industry would already mean $500 million more value added for the EU. Finally, one of the prototypes was crashed at the Technical University in Graz. Not frontally, as shown in the simulation here, but the chassis was steered with 30 km per hour against a 45 inclined ramp. The test showed no component failure. Parallel to the development of the snowmobile, a bus staircase of an entrance area of a traveling bus was designed and built for the MAN company. The task was to build a staircase from 100% organic components. Only adhesives and coating material are not of organic origin. With the developed design, it was finally possible to save almost 20% weight with the same performance. The last partner to join the research work of Woodcar Consortium was the Research and Development Department of Volkswagen. They carried out 2 corresponding research projects in Germany. In Woodcar, the research group has the task to develop a so-called body in wood of a fun car, the beach buggy. Corresponding to the other applications, all development steps took place on the computer. The final task in Woodcar will to be construct and to build the overall frame of the vehicle on a 1-to-1 scale. Magna want to challenge us by assigning us the task of developing an element that is only relevant to crashes, namely the side impact beam of a car door. This component is usually made of high-strength steel. In addition to the penetration depth, the force transmitted by the beam also play a central role in a side impact. For testing the impact beam, a new sled test setup and a test frame were developed which simulates the surrounding vehicle structure. In crash testing, the preparation time is long, but the testing time is extremely short. The prediction quality of calculation is excellent. The comparison between simulation and real test show perfect agreement. The element meets the requirements and has been successfully patented. During the various optimization loops, we ask ourselves whether we could learn from nature for crash-relevant elements. There are several structures, such as the branch-stem connection, which have to withstand extreme loads. Within the scope of a dissertation, we have dealt with such structure and have examined not only wood tissue, but also the inner structure of mussel shells and nacre. We reconstructed such a shell structure from wood and observed effects of high homogenization and increased energy absorption. The number of studies and research carried out is extremely high, so not all of them can be mentioned here in detail. We have studied the influence of weathering and varying temperature on wood and have carried out mechanical tests at -40 to +80 degrees. We have performed well over 700 screw tests and modeled the material behavior. We have described the screw holding capacity, examined the media and salt resistant of coated and uncoated laminated wood samples, examined adhesives on a microscopic and macroscopic level at different temperatures and describe adhesive bond lines in FE modeling. We developed new tests with advanced measuring devices to observe the shear behavior and to measure Poisson's ratio of solid wood. And most importantly, an amazing high number of material tests were carried out to describe the material behavior of beech, birch and poplar. The amount of work necessary was far underestimated. If we had to repeat the mechanical tests, we would only do so with the help of an automated universal testing machine that would automatically test this large amount of sample material. The data management alone was a challenge. A database was set up at Bocaux specifically for this purpose. With modern data processing and new solution for digitalization, we are moving towards the Planet Research Project Carpentier. The letters CAR stand for Computer-Aided Research and TIER means supplier in the automotive industry. With this research project, we want to show that the digitalization process, the inhomogeneous material wood can be controlled even with high product requirements and strict quality specifications. We do not only want to create digital twins of the individual components for dimensioning and technical design, but also to describe the individual production processes using digital models. This will enable us to improve, control and monitor the production processes. Laminated wood and wood hybrid materials, meaning wood components in combination with plastic and metals, as well as with other materials, including fiber-reinforced materials, will be the focus of future research work. The core of the research program is the so-called function-oriented process control. All possible influencing variables are to be recorded and described by physical models. This requires further research work in the field of material science, process engineering, quality control, and simulation. In summary, after 5 years of research, it can be said that wood can also find its place in the mobility sector. Future research will focus primarily on the production process, thus creating the basis for industrial production according to required standards. A new safety concept and the combination of human skills and knowledge and the computer technology will shorten development times and reduce costs. In addition to the areas of application targeted so far, we are convinced that the newly developed competences of the consortium will also create new markets for the material wood in the long and medium term. I would like to thank you for your kind attention. Many thanks also to my colleagues for the excellent cooperation, and many thanks to our companies and industry partners as well to all sponsors for their support.